Hey guys, my name is Frank, and this is the Python Programming video log. Today's video is going to be on platforming AI, so I'm just going to have a couple different AIs that I programmed from scratch. So hopefully you guys learned something. If you do learn something, go ahead and like the video because that helps me out a lot. Also subscribe to my channel so you can get my videos. I'm trying to release one every week, so stay tuned because I'm going to have more videos coming out soon. Alright guys, so today I'm going to be programming some platformer AI behavior, and I don't have time in this video to go over how I drew the tile map or how I set up basically the groundwork for the game, but what I'm going to do is I'm going to program 5 different behaviors, and I'm going to just program those from scratch right in front of your eyes. So these functions right here are going to get filled with logic, and they're going to be handed into these player classes that you see on the screen, these different object classes, and they are going to make the players do different things. So I'm going to start with the dude. The dude is going to be this guy right here, and he is going to follow the mouse. So I already have everything set up for the mouse and the player class itself, the different values inside of it, and all I have to do is just go ahead and use those values to program some logic. So let's get to it. Let's just say dude.y plus equals dude.vy. Vy is going to be velocity y, and dude.vy plus equals gravity. So I'm adding gravity to the dude's velocity y value, and I'm also going to update the dude's y value by velocity y on every frame. So let's save and see what we get. He's going to fall straight down. I don't want him to fall off of the screen though, so what I'm going to do is say if dude.y is greater than floor, dude.y equals floor. Simple. Floor is just going to be a value right at the top of these heads right here. So what's going to happen is once the top of the head gets past the value for floor, which I think is like 160, but don't take my word on that. Actually, I can scroll down here and see it right now. Floor is 116, so I'm glad I didn't say 160. But this is 116 right here. Once the Y position, which is the top of the player object, goes past it, it's going to stop it by setting it to the value for floor. So let's go back up here and add to it. The next thing I want it to do is jump. So I'm going to come in here and say if pointer.down, and pointer is just going to be a value that corresponds to our mouse pointer. It's going to have an X position and Y position from the mouse pointer, and it's going to have a value of down, which is going to be true whenever I click the mouse on the canvas. So if pointer.down and not do.jumping, we're going to go ahead and jump. So we're just going to say do.vy equals -16. Let's see if that looks good. Refresh. When I click, nothing happens. The reason nothing happens is because I haven't programmed in do.jumping equals false, because by default when I start out and I first instantiate the dude object, his jumping value is going to be set to true. So whenever he hits the ground, he's no longer going to be jumping, so I'm just going to go ahead and set it to false whenever he hits the ground. I'm going to save that. Now he should jump. He jumps really high. That's because there's no friction restriction on his velocity, so I'm going to say do.vy times equals friction. And now he looks like he jumps a little bit more reasonably. All right. So let's also go ahead and give him something to do for X velocity. So I'm going to say, let's see here, do.vx equals pointer.x minus do.x minus tile size times 0.5. And I'm also going to multiply that by a tiny amount, so 0.1. Cool. Okay, so what tile size is going to be the size of each one of my sprites. So this is basically going to be the equivalent of saying the pointer's X position, so say this is right here, minus the dude's X position, which is going to be right here, minus tile size times 0.5, and this actually probably should be plus tile size times 0.5, so let's try that instead. And tile size is just going to be the width and height of the player sprite. So here's the sprite. It's 16 pixels wide by 16 pixels tall or high. So tile size is basically going to just replace a width and a height value for the player because all the sprites are the same size, so I only need one value for it. So let's go ahead and update the x position as well. So dude.x plus equals dude.vx. I'm going to go ahead and save, refresh. Now when I click, he's going to move, but this is wrong because I'm just guessing here at this point. Let's refresh and see what happens here. Now his center is going to move right to my mouse point on the x-axis. And that's kind of what I want. That's what I want for the movement anyway. So he's also jumping as many times as I can click as long as he's in the air. So what I'm going to have to do here is, in addition to setting jumping equal to false here, inside of the jump condition, I'm going to also set dude.jumping equal to true. And now he's no longer going to be able to jump infinitely into the sky. So right now you see what's going on. He's jumping infinitely into the sky when I click the mouse. Now I'm clicking as many times as I can, and he can only jump one time, and only after he's landed. So that's that. So this is the player. He jumps around, he moves. Oh, actually, you know what? I want to do something else too. I want to say only jump if the mouse is above the player. If the mouse is below the player, don't jump. So I'm going to add a condition here, and if pointer.y is less than dude.y. So if the pointer is above the dude, go ahead and jump. If the pointer is below the dude, don't jump. He's moving really fast on the ground too, so I think I'm going to change that as well. So I'm just going to say if dude.jumping, then dude.vx is going to move that quickly. But if dude is not jumping, so else, if dude is not jumping, dude.vx or vx is going to be equal to pointer.x minus dude.x, same distance between pointer and the center of the dude minus tile size times 0.5. I'm just going to multiply it by a much smaller number, so 0.025, let's say. So now instead of moving super fast everywhere, he is going to move a little bit slower all on the ground. I think I like that a little bit better. There's a little bit finer control. He can still move pretty quickly if you're moving him all the way across the bottom, but not super quickly. And when you're moving close, he's not moving super fast or anything like that. So that's going to be my player movement right there. Pretty good. He jumps pretty much right to where you want him to, right underneath the mouse. Probably not the best controls for a platformer, but this is just a simple example. You could tweak the controls how you want, but this is basically how the dude behavior is going to look. So let's go ahead and program next. Let's see. Let's do something fun. Let's do the block. The block is actually going to be really cool. So let's go up to the block and get to work on the block behavior. Now the block has a couple values. It has an anchor Y value, which is going to be its base Y position because it's going to drop. And it's going to have to go back to that base Y position. So it also has a velocity Y because when it drops, it's going to go ahead and start increasing velocity Y with gravity. And it's also going to have a state in which it has to rise back up. So let's go ahead and make a switch statement for the 3 different states that the block can be in. Block.state and case waiting, case falling, and case rising. There we go. So in the case of waiting, what's going to happen is it's going to check to see if any of the other objects is underneath it. So I'm going to have to loop through the array where I define all of my different objects. So if I come down here, I'm going to show you where I define that past the tile map and for friction and gravity, which I've used so far. Right here is going to be the players array. Now I'm just calling their constructors, so block, dude, fox, ghost, and all I'm passing in is the x value, the y value, and the behavior function that I want the object to execute on every frame. So I'm going to loop through this array that has all my different objects in it, and I'm just going to check to see if those objects are underneath my block. So in the waiting state, I'm going to say for let index equal players.length minus 1 index is greater than -1 minus index. I'm going to loop backwards through players array. I just prefer to loop backwards, no real reason. All right, so now I'm going to say let player equal players index. It's going to get me my player. I'm going to say if player.x is, let's see here, if player.x plus TileSize times 0.5, that's going to be like if the left side of the player plus half of the player's width. So basically, if what this is saying is if the center of the player is greater than block.x, so the left side of the block, or player.x plus TileSize times 0.5 is less than block.x plus TileSize. So if the middle of the object underneath the block is greater than the left side of the block, or if the middle of the player underneath the block is less than the right side of the block, then we're going to go ahead and set the state of the block to falling. We're also going to go ahead and break out of the loop because we no longer need to continue in the loop. So I'm just going to say return. All right, so before we can test it, we have to go ahead and program stuff into falling. So let's go into falling. I'm just going to say this.vy plus equals gravity. This.y plus equals this.vy. Same thing that we were doing to make the player fall. This.vy times equals friction. We're going to do the same method for collision. If this.y is greater than floor, then this.y equals floor. And we're going to go ahead and say this.vy equals 0. We're also going to say this dot, oh, actually, why am I using this? I went for this all of a sudden, but this should actually be blocked. This dot state equals rising. And this up here, block.state equals falling the string. So let's see if this actually works. Okay, so he falls right away immediately, but the collision works, so that's good. So let's see why he's falling. So player is going to be, oh, I know why he's falling, because he's actually checking against himself. So easy fix. Let's go ahead and just check to see if player is equal to the block itself. So let's just say if player equals the block, return. Or actually, don't return, but continue. All right, so that little statement right there is going to ensure that we are not checking the block against itself in this if condition right here. Now I'm going to refresh. Nope. Still waiting. What could be the problem? Okay, let's do some troubleshooting. So we're looping through our players. We're getting the player value from the players array. We're checking to see if the player equals block, and we're saying continue, but what we should be saying is, yeah, continue. Okay. Let's go ahead and do a console.log down here. And we're going to put this console.log inside of that right there. We're going to see what players are actually being tested against. So the spike object is actually triggering the block to fall. So let's go ahead and see what's wrong with our code here. We're saying if player.x plus TileSize times 0.5 is greater than block.x. And, this should be an and not an or. That was my mistake. Okay. Let's go ahead and check this out. So now everything should work. And as soon as the player goes under, the block's going to fall on the player. The player that went under him is dude, and that is true. So now we don't need this console.log anymore. But what we do need to do is continue programming the block logic so he will rise up again right after he's hit the floor. So now what we're going to do, in the case that the block is rising, is we're going to say block.vy minus equals, let's make it a small value like 0.1 if block dot, oh wait, we actually have to add vy to block.y. Block.y plus equals block.vy if block.y is less than block.anchor y, which is just going to be equal to the position that the block is in when it starts. If block.y is less than block.anchor y, block.y equals block.anchor y, block.vy equals 0, and block.state equals waiting. Okay, so that should work. Let's go ahead and test it out. So the block is up here, it's waiting. When the dude object moves underneath it, just ever so slightly, it's going to go ahead and fall. It's going to rise back up. It's rising back up way too fast for my taste. Block.vy minus equals 0.1. Let's go ahead and say that. Instead of minus equal, let's just set it equal to negative 0.1. Oh, what's going on here? Why is it syncing? Block.vy, oh, because the, let's see here, velocity is not equal to 0. Block.vy equals 0. Plus equals block.vy. A little bit of troubleshooting here, but this happens when you're writing code. I mean, you're never going to get it right the first time. Sometimes you will, but most of the time you're going to run into tiny problems with your code, and you're going to have to tweak it a little bit. So in the case of rising, we're just going to subtract vy from y. So this should actually be negative, and like I said, it's usually just a tiny mistake, and you just got to tweak it ever so slightly. So in this case, it was, I had a positive value instead of a negative value. And now my block is going to rise up very slowly, too slowly actually, so I'm going to increase that to negative 2.5. That's a little bit better. It's still kind of slow. So you know what? Maybe not too slow. Let's go to 0.5 and see how that looks. Maybe a little bit too fast, but you know what? I like that. It's going to give him some more action. But basically, anytime a player walks underneath the block falls down, and that's a pretty cool functionality for a game to have. So I thought I'd put that in there because that's a cool one. So anyway, let's go ahead, and now that we've programmed the dude and the block, let's move on to the fox. Let's go down to the fox function. And what the fox is going to do is he's just going to go ahead and follow the player. So down here, or actually first I have to go up because I don't think I put this in the fox class. I'm going to go up to where the classes are. So let's see, fox class. Fox class is going to have a target. This dot target equals undefined. But eventually it will be defined, and that's going to happen in a second. So I'm going to come down here to my players array where all my players are instantiated, and I'm going to go right underneath it. I'm going to say players2, which is the value of my fox dot target equals players1, which is going to be the dude. Okay. All right, so now my fox has a target to work with, and I'm going to come into the fox behavior function. Let's go ahead and get to coding. So I'm just going to say fox.vx equals fox.target.x minus fox.x, fox.x plus equals fox.vx. And I'm also going to go ahead and decrease velocity x of the fox by friction. So I'm going to say fox.velocity x times equals friction. Let's see what we get. Get some really, really close movement. So we don't want the movement to be that close. We want the fox to kind of follow behind the player, and we don't want him to really be able to catch up to the player so quickly, you know? So let's go ahead and add in a condition that says if, and instead of doing just raw numbers all the time, let's go ahead and make a value for distance. Let distance distance x equal, oh, I went right back down there again. Let distance x equal fox.targetx minus fox.x if, well, let's not call it distance x, let's just call it d for simplicity's sake. If d times d, and this is going to get distance squared, which is great because the square of a distance, if distance is negative or distance is positive, the square of it is going to be positive. So now we don't have to worry about which direction we're moving, left or right, negative or positive. All we have to worry about is the amount. So if distance times distance is greater than, let's say 2,000, or actually let's say 1,000 for the sake of explanation, because 1,000 is, actually no it's not. Let's use 100. 100 is 10 squared. So this is going to give us a distance of 10 pixels. So if the fox is more than 10 pixels offset from the player, we're going to go ahead and move him. And this isn't going to be what we stick with. Oh, actually that's not working. Oh, because we're not saying fox.vx just yet. So fox.vx equals d. Now let's just do fox.vx equals d, and let's see what we get. Times 0.5. Not really liking how that's looking there. Vx equals d times 0.5. Let's do d times 0.05 and see how that looks. That's a lot smoother right there. Okay. And the fox doesn't totally follow the player, but what I'm going to do here is just increase this square root to a nice number that I like. This is going to be the square of a distance of 2,000. Or not of 2,000, but 2,000 is going to be the square of whatever distance is. So once you get a certain distance away from the fox, he's going to follow you. I also want the fox to jump when I jump. So what I'm going to do is I'm going to say if fox.target.jumping fox.vy equals -10. And also fox.jumping equals true. Not fox.jumping. So if the fox isn't jumping and the player is jumping, fox.jumping is going to be set to true. Fox.vy is going to be equal to -10. And also we're going to have to do some gravity here. So I'm going to do fox.vy plus equals gravity. And actually the Vx should be plus as well. Vx plus equals this. Vy should also be multiplied by friction, so fox.vy times equals friction. Ah, look at that choppy movement there. What is going on with this? That is way too choppy. I'm not sure why that's happening. If the distance squared is greater than 2,000, fox.x is going to be... Oh, you know what I'm doing wrong? This is what needs to happen. There we go. That should probably help out a little bit. Fox.x plus equals fox.vx. Fox.y plus equals fox.vy. Of course, now when I run this, the fox is just going to fall right through the floor. So what I need to do here is I need to add some collision detection with the floor. If fox.y is greater than floor, fox.jumping equals false, fox.y equals floor, fox.vy equals 0. That's going to do it for the collision detection. See what we get. Kind of like jumping after the player there. Jumping around really fast there. Like way too fast. So we're going to have to do some tweaking to that as well. Okay. Distance is going to be equal to fox.target.x minus fox.x, fox.vy plus equals gravity. If distance squared is greater than 2,000, let's do 1,000. If distance squared is greater than 1,000, fox.velocityx plus equals distance times 0.5. We're going to do equals distance times 0.5. Let's actually make that 2.5 to make it smaller. If fox.target.jumping, so if the player is jumping and the fox is not jumping, the fox is going to be jumping, and the fox's y velocity is going to be set to -10. Fox.x plus equals fox.velocity x, fox.y plus equals velocity y. Let's go ahead and see what this looks like here. A little bit more reasonable. He's going to be jumping, but he's not really going to be jumping to where the player is very nicely. I don't really care for that. So let's go ahead and say if fox.jumping, we're going to set one velocity for him, and if the fox is not jumping, we're going to set another velocity for the fox. So if the fox is jumping, we're going to go ahead and set actually this is going to have to be where this goes, because he's only going to follow the player if the player is greater than a squared distance of 1,000 away. So let's go in here, just move everything right inside of here. If the fox is jumping, go ahead and set his velocity x, else, there we go. Else we're going to do what we had. So if he's not jumping, we're going to do what we had set for velocity x. If he is jumping, fox.vx is going to be equal to, let's see here, plus equals d times 0.001. That might not look good either, but we could always tweak it again. Probably a little too small, so let's go ahead and back this up by 1. I like that a little bit better. Like I said, it's mostly tweaking, so I like that a little bit better. Let's go ahead in here and say 2.5. Now he's like right there jumping towards the player. So I like the following. I think it's pretty cool. You can change this however you want. Basically, you're just going to get the distance from the target to the object that you're going to have follow the target, and you're going to gradually decrease the distance between them by, a small amount of that overall distance. And for jumping, if the player is above, or the target is above, that's a little bit too fast there. It's like way too fast. It's kind of crazy. It's like some crazy following right there. But anyway, you get the idea. You could tweak this a whole bunch and make it work, and you could change stuff around a little bit and make it work. Let's move on to the ghost. So the ghost is pretty cool. I like the ghost probably the most, just for the effect it has. The ghost is going to move around to a random position inside of the map. So let's go ahead and say if, actually let's not start with the if statement. Let's go ahead and say ghost.x plus equals ghost.vx ghost.vx equals ghost.destination x minus ghost.x. So once again, I'm just going to be decreasing the distance between his destination point and his current position on the x-axis. I'm going to go ahead and here I'm also going to say ghost.vx times equals friction. And he's not ever going to jump, so he doesn't need to fall, so I'm not going to do any vy stuff with him, or velocity y, or update his y position. So far he shouldn't do anything because destination x is set to equal his x position when he's instantiated. So they're not actually going to do anything yet, but let's go ahead and say if ghost dot, actually let's go ahead and get a distance value in here again. Let d for distance equal ghost.destination x minus ghost.x. You can add distance times a very small amount to velocity x for the ghost. So if d times d is less than 100, which is 10 squared, so if he comes within 10 pixels of his destination, then we're going to go ahead and say ghost.destination x equals math.random times map columns times tile size. So if I have tile size, which is one tile, multiplied by the number of tiles or columns in my map, it's going to give me the entire width of the map. So basically, that's going to make my ghost choose a random location between the left side of my map and the right side. But since the x position of the ghost is going to be his top left corner, if his destination is all the way over here, he's actually going to go off screen. So what I'm going to do is set it to that minus 1 tile size, which is going to be the ghost's width. So now let's see what this looks like. My ghosts are moving around. They're getting to their location and they're sliding to their next destination, because every time they get within 10 pixels of their destination, they go ahead and they move towards a new destination that is randomly selected from between the left and right side of my map. And as you can see, as the ghost moves underneath the block falls down because it's detecting that a player is underneath it. So let's check that out right here. Bam, right on top. Okay, so that works pretty well. Now what I want to do is I don't want them to move super fast. I kind of like the way it looks, but I don't want them to be able to move way too fast. So what I'm going to do is I'm going to come in here and I'm going to say if ghost.vx is greater than, let's say 3, ghost.vx equals 3, else if ghost.vx is less than 3, less than negative 3, ghost.vx equals negative 3. And to prove what this is doing, I'm going to go ahead right here and I'm going to make their movement speed a lot faster. I'm going to comment out these lines. So what I'm doing is I'm basically clamping the movement speed if it goes over a certain amount. So right now they're moving really fast because I made this value right here very small, or actually a lot larger than it was. So now they're moving a lot faster to their destination. But if I go ahead and remove this right here, should clamp their movement speed to 3 pixels. I want that to actually be a little bit less, so I'm going to say 2. You know what, even 2 is too fast. I'm going to say 0.5. Alright, now they're moving nice and slow, but they're moving at a constant rate. I'm going to go ahead and slow this down, and I'm going to go ahead and, actually, I'm going to decrease. I'm going to leave it the same. That should be good. Now they kind of move nice and slow, and when they get closer to their destination, they kind of ease to a stop until they get within 10 pixels of their destination. And actually, I am going to decrease this. I'm going to make this 4 pixels, so the square of 4 is 16. So when they get within 4 pixels of their destination, they are going to change direction. And that's going to allow them to slow down even more as they get close to their destination. Almost like they're thinking about their next move when they get to their final destination there. Okay, so now the last 2 things I have to do, and I'm not too happy about the way that fox is moving, but I want to move along with the video. So what I could do is I could take this, and I could just go in here and say copy, and this is what I'm going to do. I'm going to come up into the fox. I'm going to say paste. I'm just going to replace ghost with fox. I'm going to clamp his velocity. If fox.vx is greater than, I'm going to increase this as well. I'm going to make this 4. But like I said, this is just a lot of tweaking. You just got to get the right numbers. Okay, so now the fox isn't like going crazy, but he is jumping after the player and he is moving after the player, and he does have his distance, so I like the look of that a lot better. That's pretty cool. And I got my ghost moving around as well. Now let's go ahead and program the different behaviors for these spikes. So let's go for spike A. I'm not sure which one that is, but basically how this works is inside of the spike class. Let's go up to the spike class real quick and see what we're working with here. Got to go past all this code I just wrote. Spike. Okay, so the spike has an anchor X, an anchor Y, a D, which is going to be a direction in radians, and a range. And the range is going to be the distance that it moves around its anchor point. So let's go to spike A and make it do something. Come all the way down here, spike A. All right, here we go. So spike.d plus equals 0.01. Let's make that what it is. Then we're going to say spike.x plus equals, or actually spike.x is going to be equal to spike.anchor x plus math.cos or cosine of spike.d times spike.range. All right. Let's see what happens. And we have movement back and forth. I don't like how slow it's going though. So let's go ahead and say increase the amount that the direction changes. And now we have a nice spike moving back and forth on the x-axis. And if you remember how this works is, if you remember back to your, I'm not sure what it was, but some high school math class where they taught you about polar coordinates. D is just a direction in radians. And cosine converts polar coordinates or radians to an x value or an x coordinate in Cartesian coordinate system. So basically I'm taking a direction in 360 degrees and I'm getting the x value of that direction and I'm multiplying it by spike.range. So if I were to make this less and say 10, the range of this would decrease to 10. So let's go ahead and refresh. Now the range is going to be a lot tighter. But basically what's happening, just imagine a circle going around here. As the spike rotates, there's a circle that it's rotating on. I'm kind of tracing it with my mouse, except it's just clamped to the x position. Now, if I were to come in here and say spike.y equals spike.anchor y plus math.sine or sin spike.d times 10. Let's make it the same. Refresh. Now I would have that full circle. Pretty cool. So let's go back to spike.range. Now I have an ellipse. So let's make it an ellipse that is half as wide as it is tall. So I'm going to do spike.range times 0.5. That's basically going to give me 10, exactly what I just had. So now I have that nice ellipse there. And for spike B behavior, I'm going to do basically the same thing. I'm just going to do it in the opposite direction. So let's come in here. paste that. And go ahead and say, make the X range 0.5 and make the Y range full. Alright, so now I have a couple of spikes. Looks pretty cool. They don't do anything when they hit the player, but they could if I were to take it there and program collision in. But basically, this is just a couple of basic behaviors, and I think I have a pretty good way of doing the behaviors and mixing the behaviors with the different objects, because all the objects are basically the same. So let me go ahead, as the last thing I do in this video, I'm going to show you how I'm linking these behavior functions to the actual object classes themselves. So what's happening here is I'm defining these objects right here, and I'm handing in those different functions that I literally just programmed. And what's happening is, up inside the class, when it gets instantiated, let's go to, it's a good one. Let's go to the top. Let's go to block. Oh my gosh, I have to go even farther, all the way up to the top. Let's go to block. Okay, so when I'm instantiating it, I'm handing in the X and Y position of the block, which is going to be right here, and I'm handing in that function called block behavior into this parameter right here, behavior. So inside of block, I have a superclass calling its constructor, and that superclass is the player class. So it's going to take the X and Y position. It's going to take 160, which is going to be the source X position of the block. So this is going to be 160 on the X axis inside of this sprite sheet. And it's also going to take the behavior, and it's going to use this information to place the sprite and get the blit position of the sprite image inside the image, and this is going to go ahead and be the behavior for it. So this is the player constructor, and it does just what I'm saying. It keeps track of the X and Y position, the source X, and it has a pointer called behavior to the behavior function that I hand in. So now this is the actual block constructor, and it's going to do that. It's going to apply all that stuff from the player class. It's also going to define the values that the block actually uses to do its thing, and it's also going to inherit from the block prototype. So the block prototype is going to be inherited from the player prototype, or that's what I meant to say. It inherits from the player prototype rather. So the player prototype is right here. It has one function called behave, and that function is going to call this .behavior, which is going to be equal to whatever we hand in as the behavior, and it's going to call behavior and pass in itself. So the reason I have it set up this way is so you can port the code to a strongly typed language like Java or C++. Because JavaScript does type conversions for you, but if you're working with C++ or Java, you're not going to be able to get away with that. So this code, the reason I'm doing it like this and it looks kind of funny is because it will be easily portable to a strongly typed language. So let's go down and take a look at where the behave function is actually called. When you call behave, it's going to call the function, the actual behavior function, the ones that I was programming, and it's going to hand in itself. The object itself is going to be handed in. So that's why inside of these functions, instead of using this, for instance, to reference the dude, I'm going to be using the dude parameter. And that's why I'm not using this here. When I go all the way down to the game loop, if I can actually scroll that far down, when I come all the way down to the game loop, I'm looping through all my players. I'm just going to call player.behave. And this is great because I can put all my players, no matter what their type is, into an array, and I can call all these different behaviors just from one function call. So this is great because instead, if I didn't do it this way, if I didn't have this set up the way it's set up, what I would have to do is I'd have to have a separate array for spikes. I'd have to have a separate array for blocks. I'd have to have a separate array for the ghost and the fox, and I'd probably just have one dude object because he's the main player. There's only going to be one of him. But I would have to loop through all those arrays separately and call their individual behavior functions. Whereas now I only have to call one function called behave, and what behave does is it calls the, if I scroll all the way back up here to behave, let's see where it is. What behave does is it calls the pointer to the specific behavior function and passes in the object itself. And this prevents me from having to have a whole bunch of parameters for, say, for the fox, I don't have to pass in a parameter for target. Or say for the player, rather, I don't have to pass in a parameter for pointer. I just have to pass in this. And then these actual behavior functions operate from almost the global scope. Because, let's see if I can find the dude behavior. They kind of operate from the global scope because dude behavior is pulling in variables like gravity, which is a global variable, friction, that's a global variable, pointer, wherever that was, pointer is also a global variable. So I can have these behavior functions have access to everything I need, and I don't have to hand in, or I don't have to create a bunch of unique parameters for my behavior function. This allows me to have a whole bunch of different types of behaviors that have a whole bunch of different inputs, but I don't have to call them from separate loops. I can call them all from one loop. I can define them all in one big array, and I can update them all with one simple function, and then go ahead and draw them. So all of that code inside of my game loop is being called right here. I'm looping through all the objects. I'm calling one function that they all have that calls a pointer function to a unique behavior, and it hands in the object itself into the behavior function, and it executes the behavior on the object. So that's the reason I set this up this way. Not only is it easily portable to a strongly typed language, but it also allows me to only have one function to work with, the behave function. So anyway, that's how I program my AI for different characters. It's very easy to grasp once you actually program it. It's not that hard. I like the way it works anyway, and it's great because you could port it to a strongly typed language. So I hope you guys learned something, and that is how to program behaviors for platforming AIs. So just an additional note here, I actually forgot to add these math.rounds in, and this is on the draw function that draws all the different sprites. So what the math.round does is it will just clamp my player's X and Y positions to whole numbers when I draw them. And what that's going to do is give me a very nice, crisp looking graphic on the screen instead of having it interpolated between two different pixel positions. So right now, if I take a look, everything looks really crisp. I just removed those math.floors. I'm going to go ahead and save, and when I refresh, things are going to look kind of blurry. You can tell that they're not as crisp anymore. The fox, particularly if you look at this guy or at the ghost right there, they're just blurry. So you want to have that math.floor in there. That's going to definitely make your graphics look a lot crisper, and that's definitely going to be an improvement for you. So anyway, in conclusion, that is how I do my AI behavior for a little platforming game. It's a pretty good method. I think it can be ported to a strongly typed language anyway, so that's a benefit right there. If you like the video, go ahead and give me a like and subscribe. This way you can catch my next video, and I'll see you guys next time.